Yes.
Okay.
All right. Then I guess we can get started. Another talk, I guess, from Majid's group. Um, this one from TUM. Bingzhuo will be presenting.
Yeah.
Go ahead, Bingzhuo.
So thank you very much. So good morning, good afternoon, and good evening, depending on where you are. Welcome to my talk about my research for how to construct Safe-visor architecture for uncertified controller in stochastic cyber-physical system, which can be applied for achieving trustworthy AI. So here is the motivation for my research. So in modern cyber-physical system, many AI-based controllers are expected to be used for accomplishing complex tasks. But then there will be a problem. It is very challenging to ensure safety when this kind of controller are applied because it is very difficult to formally verify this kind of controller. Therefore, to tackle this issue, we exploit the idea of sandbox from the community of computer security. In general, the untrust component here is isolated from the critical part of a host machine, and this component can only access to the critical part when you follow the rule given by the sandboxing mechanism. So here we do some similar thing to this AI-based controller. Namely, we try to sandbox this AI-based controller to achieve both functionality and safety. So here is the overview of our proposed architecture. The AI-based controller is in general placed in the sandbox environment here. And there is a safety advisor in this architecture, which only focusing on maximizing the probability of fulfilling the safety property of interest. And every time instant, the supervisor checks the input provided by the AI-based controller. And if the input provided by the AI-based controller is hazardous, the supervisor will feed the input provided by the safety advisor for controlling the plan instead of the one provided by the AI-based controller. So note that here we consider off-the-shelf AI-based controller, which means that we do not focusing on how to design the AI-based controller, but treat the AI-based controller as given. They can be trained by arbitrary methods, is a backblock controller. Accordingly, we focus on how to decide the safety advisor and supervisor regarding the safety property of interest. So later I will formally define what does it mean by safety property in my current research. So in my work, I focus on discrete time stochastic system in this form, in which var sigma is a sequence of IID random variables. And this kind of system can be equivalently written as a general Markov decision process, abbreviation GMDP, in which the stochastic kernel characterizes the transition probability among different states with different input according to this dynamic. And this is the system model we are using. And next, I talk about what kind of safety property we are interested in when designing the safety advisor and supervisor. So here we focus on properties that can be modeled by deterministic finite automata. So some of you may not be so familiar with this kind of finite automata. So here is an example. Consider the following safety property. If the system starts from region R1, it should avoid R3 before it has been R2. This safety property can be modeled by the following DFA along with a labeling function like this. This DFA accepts all the back prefixes that violate this property, and Q1 to Q4 are states of the DFA in which Q1 is the initial state, and P1 to P4 are the atomic proposition of this DFA. And the labeling function here maps the output of the physical system to some specific atomic proposition. Additionally, the dynamic of the system drives the evolution of the DFA with the help of the labeling function. And here is an example. Consider the current state of the DFA is Q2, and the current output of the system belongs to region R2. What is the next state of the DFA? So Q3 is the next state because Ly equals to P2 and there's a transition from Q2 to Q3 with P2. Note that for every DFA, there is a special state called accepting state, which is the state with double circle. Depending on what does it mean by the accepting state is reached, we focus on two different types of property. For some kind of properties, reaching the accepting state means satisfaction. For example, those that can be modeled by code-safe linear temporal logic on finite traces. The satisfaction of this kind of property can be verified in terms of finite traces. And accordingly, we focus on the problem of robust satisfaction, with which we want to find a lower bound for satisfaction regarding this kind of property. In some situations, reaching the accepting state may mean violation. For example, those can be modeled by safe linear temporal logic on finite traces. For example, this is an example for this kind of property. Accordingly, we focus on problem of worst case violation, and we expected that we can find an upper bound for the violation probability. So here is how we formulate our problem in this research. So we define a parameter eta, which denotes the maximum tolerable probability of violating the desired safety specification. This parameter can be used to achieve compromise between functionality, which is provided by the AI-based controller, and safety. Concretely, the larger is eta, less interference will be applied to the AI-based controller so that the AI-based controller have more opportunity to access the plan. But at the same time, you will have a lower probabilistic guarantee for safety, and vice versa. As for the problem of robust satisfaction, our target is we need to make sure that 1 minus eta is the lower bound of the probability of satisfaction. And accordingly, as for problem of worst case violation, our target is to make eta as the upper bound of the probability of violation. Note that here we cannot select arbitrary eta, and we want to achieve that. It has some limitation for the selection. Consider a safety advisor with probabilistic guarantee of satisfaction rho. We should ensure that eta larger than 1 minus rho so that eta is achievable. To take away is you cannot have a higher safety probability than the optimal safety controller so that it is achievable, so that you have some chance for the AI-based controller. So here's the overview of my talk today. So I will first discuss the approximate probabilistic relation between a finite abstraction and the original system so that we can have formal safety guarantee. Then I will discuss in details how to decide the safety advisor and supervisor, and we conclude our talk with a case study. So let's start with discussing approximate probabilistic relation. Consider the original stochastic system with continuous state and input sets. In general, we are not able to directly synthesize a controller for this kind of system because there's no closed form solution for a for synthesizing controller for this kind of system. Therefore, we will construct a finite abstraction for this system. To do this, we discretize the state set and input set of the original system and accordingly construct the transition kernel. Since the finite abstraction is constructed based on the original system, they are similar. The remaining question is how we can quantify this kind of similarity and how we can make use of this similarity for synthesizing a controller. So now imagine if I'm able to keep the state of the original system and X hat the state of the finite abstraction always close to each other. Then we are able to control the original system indirectly by controlling the finite abstraction. So to quantify this kind of relation, we introduce so-called epsilon delta approximate probabilistic relation, in which the epsilon here denote how close X and X hat should be, and delta quantify the probability that given they are epsilon close to each other at the current time instant. What is the probability that this closed list relation does not hold anymore at the next time instant. Assuming that we are able to find such a relation between the finite abstraction and the original GMDP, then we are able to first synthesize a discrete controller for the finite abstraction, then refine this controller as a hybrid controller based on this relation so that the original system can be controlled. Note that the interface function here is the key component associated with this relation, such that the relation between the finite abstraction and the original GMDP can be maintained. So in the following discussion, we assume that this kind of relation can already be found between the finite abstraction and the original GMDP. And the literature list here introduce in detail how we can find such a relation for a class of nonlinear stochastic game. So let's continue with discussing how to design the safety advisor. For this design the safety advisor, we need to construct a finite abstraction regarding the original system. To do this, we first discretize the state space and input space and selecting representative point for the cells which are used to discretize this set. Based on this discrete state set and input set, we construct the stochastic kernel. Since they are discrete, the stochastic kernel can be expressed as a matrix in which each entry characterizing the probability of transition among different states with different input. For example, the entry here means the probability of reaching x3 when you start from x2 and use u1 for controlling the system. Based on the finite abstraction, we then construct a product system between the finite abstraction and the DFA that models the property of interest. For this product system, the state set is the concatenation between the x hat, which is the state set of the finite abstraction, and Q, the state set of the DFA. And the dynamic of this product system is constructed by coupling the dynamic of the physical system, T hat, and the dynamic of the DFA. And based on this product system, we synthesize a Markov policy in finite time horizon. And based on this Markov policy, we construct the safety advisor. Consider that we are able to compute this Markov policy. And here's the introduction how the safety advisor works. So here is the Markov policy that is synthesized before. And at each time instant, the original system provides its current state and fed it to the safety advisor. And based on this X, the internal state X hat of the D hat is updated based on the approximate probabilistic relation. And at the same time, the internal state Q of the DFA is updated based on the output of the original system. And based on this X hat and Q, the synthesized Markov policy provides U hat accordingly. And finally, the control input provided to the original system by the safety advisor is computed by the interface function associated with the relation between the finite abstraction and the original system. The computation is done based on U hat, X hat, and X. And the remaining question is how we can obtain such a Markov policy. Since the product system here is a finite system because the finite abstraction have finite state set and the finite automata also have finite state set. The Markov policy can be expressed as a matrix like this, in which each row denotes the Markov policy for different state at the same time instant, and each row denotes the Markov policy for the same state at different time instant. Our first task is to synthesize the Markov policy for constructing the safety advisor. To do this, we need to fill in all entries of the matrix like this for all states of the DFA by using Bellman recursion iteration. So here, the iteration is done by applying Bellman operators that also consider approximate probabilistic relation during the iteration. So the literature here provide technical details about how these operators look like and how does it work. Once we have already get the Markov policy, the second task we need to do is to obtain the safety guarantee provided by the safety advisor. So this guarantee can be obtained accompanying with the Markov policy, which means that once you have synthesized the Markov policy, and at the same time, you get that probabilistic guarantee provided by the safety advisor. So next, we discuss how to decide the supervisor for the Safe-visor architecture. Here's the high-level idea of how supervisor work. So at time instant k, the AI-based controller provide an input UUC, and we need to decide whether this can be applied to the plan. So the first thing we need to check is we need to see whether the approximate probabilistic relation still holds when you accept this UUC. This is crucial because the safety guarantee provided is on top of this relation. We need to ensure that this relation holds. To do this, we need to check whether there exists at least one element within the finite input set corresponding to the UUC provided by the AI-based controller such that the relation still holds. If no, reject it. And if yes, we continue with checking the second condition, namely whether eta is respected by accepting UUC. Since eta is our safety requirement, which characterizes the maximum tolerable violation probability, this has to be respected. To do this, we estimate the probability of violating the desired safety specification, assuming that UUC is accepted, and then check whether the estimation is smaller than the maximum tolerable violation probability. If no, reject it. If yes, we are able to accept this input. The remaining questions are how we can do this, these two steps. Consider checking the condition 1, which means that we need to see whether the relations still hold. We need to check whether there's element within this set. Here, x prime denotes the next state of the original system, and when the UUC is applied, and x hat prime denotes the next state of the final abstraction. And this part denotes the relation holds in the next time instant, so that the set UF denotes the element within the finite input set corresponding to UUC such that the condition, the relation still hold at the next time instant. As for how to check whether there's element within this set, it depends on the specific system dynamics. So here's an example for how we can do that. Consider a linear stochastic system like this, and its finite abstraction on the right-hand side. So they have the same A, B, R, and C matrices. And the beta here is the additional term introduced by discretizing the state set. And consider we have already found a relation between both systems like this. The relation holds in the next time instant can be translated as the following inequality, in which the blue part denotes the next stage of the original system, and the red part denotes the next stage of the final abstraction. And this can be further simplified to the following inequality, in which the blue part is null, since we know xk, UUC, and x hat, so we denote it by phi k. On the right-hand side, beta max denotes the quantization parameters for quantizing the original system, so that the right-hand side of this inequality can readily compute offline. So on the fly, we need to find out U hat such that this inequality holds. So this is basically how we check condition 1 for this example. If the set UUF is not empty, then we can continue with checking condition 2. And how to check condition 2 depends on what kind of problem we are focusing on. So we first discuss how we can check condition 2 for the problem of robust satisfaction. So we assume that UUC is accepted. And based on this assumption, we estimate the probability of violating the desired safety specification. For problems of robust satisfaction, violating the desired safety specification means either the accepting state of the DFA are not reached within the time horizon of interest, because in this problem, we decide that the accepting state is reached, or the approximate probabilistic relation does not hold anymore at some time instant within this time horizon. Note that the second point is also crucial because, again, our safety guarantee is provided based on this relation, so that if this relation does not hold at some point, we are not able to provide any guarantee. To do this, we need to make use of the history paths of the Safe-visor architecture, which is a sequence of X hat, Q, and U hat. Based on the history path, we can estimate the probability of the following two events. First, accepting state are not reached, but the relation still hold before time instant k, which is the current time instant. Second, the relation does not hold at some time instant before time instant k, while the accepting state has not been reached. Since we are interested in the estimation for the whole time horizon, but we do not have any information about what will happen after time instant k at runtime, when the current time instant is k. In general, we see whether eta can still be respected, at least by using the safety advisor afterwards, assuming that UUC is accepted. Therefore, we consider safety advisor is applied afterwards, and correspondingly, we compute the probability that the relation holds at the next time instant, and the probability that the accepting states are reached at some time instant afterwards, while the relation holds all the time. Based on the probability of these four events, we are able to compute the estimation like this, with the U hat star here, the element within the set U hat, which I have mentioned beforehand, such that the estimation is maximized. And then we compare the maximum estimation of violation with the maximum tolerable bound to see whether UUC can be accepted. And this is basically how we deal with the problem of robust satisfaction. And next we discuss how we can do that for problem of worst case violation. For this problem, violating the desired safety specification means either the accepting state are reached at some time point within the horizon, or the relation does not hold at some time point. Similar to the problem of robust satisfaction, we compute the estimation for the problem of worst case violation by using the history path. Based on this path, we are able to estimate the probability that the accepting state are not reached, but the relation holds before time instant k. And consider that the safety advisor is applied later on, we are able to estimate the probability that accepting state are not reached, but the relation holds afterward. Accordingly, we can compute the estimation like this. With the U hat star, the element within the set U hat that maximize the estimation of the violation probability, and then we compare the maxima estimation with the maximum tolerable bound to see whether this input can be accepted. In the end, we show the case study to show the effectiveness of our proposed architecture. Here we consider a case study for DC motor in which the angular velocity and the currents are the state of the system, and the voltage source on both sides of this circuit as the input of the system. And here we consider a safety property that need to be satisfied within 7 minutes. First, the current should be within a range, and the angular velocity should also stay within a range. And additionally, if the angular velocity reach a subset of this range, it should stay within a smaller range instead of the original range, which is 1.5 prime to 2.5 prime here. Here we consider eta, the maximum tolerable bound of violation probability, is 0.1%. For demonstration, we use an AI-based controller that is trained by DDPG algorithm for tracking the desired angular velocity. And here's our set point configuration. And here's the simulation result. We simulate the case study for 10 to the power of 5 times, and we see that when using the Safe-visor architecture, all the traces satisfy this specification so that actor is respected. Meanwhile, more than 85% of the input provided by the AI-based controller can be accepted. At the same time, if we do not use Safe-visor, none of them satisfy the specification, since during this time period, we have a set point that is close to the boundary, and the AI-based controller is currently not robust enough so that it drives the system violating the desired safety specification that is mentioned before. The last part I want to emphasize is that the average execution time of this case study is less than 1 millisecond, so that our proposed architecture can be applied efficiently for this case study. So thanks a lot. We want to acknowledge the funding that support our research. And in the end, I also list the literature that are related to my talk today, so that if you are interested in that, you can go through these literatures. Thank you.
Thank you, Bingzhuo.